Similar to exponential growth, we can look at exponential decay models. And this is when essentially the same thing is happening, but instead of growing, we're decaying. And when the decay rate is proportional to the size of our population y, or whatever quantity we're measuring, then we say that we have exponential decay. And this is the formula. You'll notice this is the exact same formula as exponential growth. The only difference is that b will now be a number between 0 and 1. And a is still the initial size of the quantity. So let's look at an example. The most common example in nature of exponential decay are when we have radioactive substances. So a radioactive substance or a radioactive element is where we have something where the actual atomic structure is breaking down over time, and so we lose some mass over time. And so this is often given as a number called half-life, which is the amount of time that it takes for a substance to lose half of its mass. So, for example, carbon-14 is one of the most commonly used substances where we're measuring decay rates because it helps us to date things. That's what carbon dating uses. So carbon-14 has a half-life of 5,715 years. A sample of carbon-14 is initially 28 grams. We'd like to find the amount left after 1,000 years. So here's what I can say. We know our general form is a times b to the x. And we know that after 5,715 years, we'll lose half of our mass. So we're starting out with 28 grams. Okay? But if I plug in 5,715 for x, I should end up with half of 28, which is 14. So now I can solve for b here. If I divide both sides by 28, I get 1/2 equals b to the 5,715. Now, raising both sides to 1 over that, I get 1/2 to the 1 over 5,715, and that's my b. Now I can take that and plug that in to my general model. So my model, I've got y equals a, the initial amount, which in this case is the 28 grams, times b, which is this fun thing, 1/2 to the 1 over 5,715. And then that b is raised to the x. And when I raise this to the x, that just means I put an x in that exponent right there. So there's our model now. We like to find the amount left after 1,000 years. So we can go ahead and plug 1,000 in. 28 times 1/2 to the 1,000 over 5,715. And now we're ready to plug this into our calculator. 28 times 1/2 to the 1,000 over 5,715. I'm going to hit Control Enter on this calculator to get an approximate there. So about 24.8. 24.8. And we want to make sure that we're always indicating units in these applied problems. And this initial amount was 28 grams, so we're ending up with is grams as well. So after 1,000 years, we'd be left with about 24.8 grams of the carbon-14 left in this sample.